Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 17 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 3405. Count the number of arrays with k matching adjacent elements. So let's read the problem statement first. You are given three integers n, m and k. A good array of size n is defined as follows. Okay, a good array of size n is defined as follows. Each element in array is in the inclusive range 1 to m. Okay, so we have given this integer m also. Okay, so here also if I choose, that element should belong to from 1 to m only. Okay, here next element it should also belong to from 1 to m. Okay, and this element also it should be from 1 to m. Okay, let's say your n is 3. Okay, in this case, right? Okay, after this, exactly k indices I where 1, okay, where I value it should be greater than equal to 1 and less than n. Okay, it should satisfy the condition array of I minus 1, it should be equal to array of I. Okay, so let's say your k value is 1 here, right? So let's suppose here m value is 2. So here let's say we have 1 and 2. All right, so here if you see in this case, this is a good array, right? Size is equal to n, okay, 3, and m is equal to 2. That simply means that we can use elements from 1 to m, so we can use 1 1 or 2. Okay, and here exactly k indices, okay, let's say your k is 1. So see, exactly k indices I where I value it should be greater than equal to 1 less than n, it's satisfying the condition array of I minus 1 is equal to array of I. Okay, so here if you see at this particular position, if you are here, so here at this case array of I minus 1, okay, this element is equal to this element, right? So exactly one position. Here if your I is here, so then these are not matching, so there is only exactly one indices, right? One value of k, right, where both are matching. All right, okay, so we have to return the number of good arrays that can be formed, and since the answer may be very large, we have to return it modulo 10 to the power 9 plus 7. All right, so now see this example number 1. N is equal to 3, m is equal to 2 and k is equal to 1. Okay, I think this same example, n is 3, m is 2, k is equal to 1. Okay, so here there are four good arrays. They are 1 1 2. Okay, we already discussed about this 1 1 2. Okay, and see here 1 2 2 also is fine, right? So here both are matching. Okay, right, and size is 3 and we are using just 1 to 2. Okay, here also this is good array and this is also good array, right? Hence the answer is 4. Okay, so we have to just return the total number of good arrays, so 4 is the output. Okay, so how we are going to solve this problem, right? So let's see, let's do one thing. All right, so here we have to form one array, right? Good array, right? So in this array we have n number of elements should be there, right? Okay, so here let's suppose these n number of elements are like this, a b c c. Okay, let's suppose these are the n elements, right? This is of size n. Okay, n is nothing but 5 in this case, right? Okay, so we have to find the adjacent ones, right? Array of I minus 1, it should be equal to array of I. Okay, adjacent ones. So here this is n. Okay, n value is 5 and we are dealing with adjacent ones. Okay, array of I minus 1 is equal to array of I. So I can say that this we need to check. We need to check this one, we need to check these two, and we need to check these two. So in total there are 4 square boxes, 1 2 3 4. That simply means n minus 1 we need to check. Okay, we need to check how many n minus 1 adjacent values. This is what we need to check. Okay, among these n minus 1, it is saying that k should be should be the case where array of I minus 1 is equal to array of I. Okay, so among these n minus 1, okay, among these n minus 1, k should have equal elements. Okay, k should have equal elements. So let's suppose k is equal to 1. So let's say this is having equal. So what are the remaining ones? Okay, total n. Among them, it is saying that total n minus 1. Okay, total n minus 1. 1, 2, 3, 4, n minus 1. Among them, it is saying that k should have equal value, right? Exactly k indices which satisfy this condition. Okay, so how many are not satisfying this condition? So can I say that n minus 1 minus k, okay, right? Total among them I subtracted this, so I will get this n minus 1 minus k. So I'm saying that n minus 1 minus k are not satisfying this condition, and this is right. Okay, so 5 minus 1 4, 4 minus 1 3. Okay, so yes, 1 2 and 3 are not satisfying. Okay, nice. 3 are not satisfying. Okay, here let's say this is d. Okay, you are going to say that this is also satisfying. Okay, let's say this is d. Okay, so now these are equal, and here b c d. All right, and okay, let's do one thing. Let's make it a little bit more interesting. Let's use it c only, and now if you change it to 2, okay, let's say your k is to 2. So in this case, if you see, this is matching and this is matching. Okay, total 2 are matching. So how many are not matching? N minus 1 4, 4 minus 2 2 are not matching. So which one are not matching? This is not matching, this is not matching. Okay, b and c, a and b. Okay, these are not matching. All right, so let's see this case only, right? Let's pick this example, a b c c. All right, so now here among n minus 1 minus k, okay, we are getting 2. Okay, so let's divide this. Okay, let's divide this array in n minus 1 minus k partitions. Okay, uh, we are going to split this array, right, using this n minus 1 minus k value, right? So how we are going to split that? So here if you see, a is matching with a. Okay, a is not matching with b, and then this box b and c, b is not matching with c, and then cross this, c is matching with c. So what I'm going to do here, I'm going to split this. Okay, I'm going to make one line here. Okay, I'm going to divide the array, and I'm going to make one line here. So if I do this, so now if you see, this is one line, this is one line. Okay, a and b, among them there is one line, and this. Okay, so how many number of lines that I'm doing here? I'm drawing this n minus 1 minus k number of lines. Okay, so now how many splits are there then? Okay, so this is one split, this is one split, and this is one split, total 3. So can I write uh, here, can I write that as n minus k only? Okay, just remove this minus 1, because now if you do n minus k, n is nothing but 5, k is 2, 5 minus 2 3. Okay, so here 3 segments are there, 1 2 and 3. Okay, I'm dividing. Okay, I'm doing the partitioning on this n minus 1 minus k. Okay, where value is not equal, right? I'm doing the partitioning among them, but we are getting n minus k. Okay, n minus k segments. So here if you again write this, so what we are getting? We are getting a, this, we are getting b, and we are getting cc, right? Okay, so total 3 are there. All right, okay, so now from here one thing is clear now, that if one thing is clear, that in these segments elements are equal. Okay, if you see, this is segment 1. Okay, all the elements are equal. In this segment 2, all the elements are equal. In this segment 3, all the values are equal. Okay, this is clear, right? Okay, now here in the segment 1, if you see, I have m number of choices, right? I have m number of choices in the segment 1, right? We can use 1 to m any value, right? 1 to m any value. Okay, for this first one we can choose any value, right? Okay, so first segment choices is, let's say, m. Okay, m choices. Here if m value is 2 na, right? So here if I do this, so here I can choose 1 1. Okay, in this segment. Okay, or I can choose 2 2. So I have two choices, right? 2 is nothing but m choices. Okay, so I can say that in the first part I have m number of choices. Clear? Now in the remaining segment, how many choices I have, right? So in the remaining segment, if you see, if I have m here, so definitely this should be different from this one, right? Okay, so here I have just single choice, m minus 1 number choices, right? M minus 1 number of choices I have, right? Because this should be different, this segment value, okay, it is starting from here, it should be different than this one, right? Otherwise these two will be matching now. So here we are, there is segment, right? So this value should be different. So how many choices I can say? I can say that I have m minus 1 choices. So that is right here. If you see this example, here 1 1, so here we are using 2. Okay, so if I use 2 2 here, then next time I'm using 1 here, right? Clear? Okay, so here we have how many choices? Remaining segments we have m minus 1 choices. Okay, and these m minus 1 choices we have for how many these how many among these? Okay, so in total these are nothing but n minus k. Okay, n minus k 3 segments, n minus k total segments. Among them, here I am giving 1 choices, like here I am giving m choices, okay, for segment 1. Remaining segment is n minus k minus 1. Okay, these are the remaining number of segments. Okay, so for this, okay, for this I can simply write it as, for first segment we have ways to choose, first segment we have m choices. Okay, then for this other half I can say that I have m minus 1 choices for how many? For n minus k minus 1 segments, n minus k minus 1. Okay, for this, just for one only we have m. Okay, for other one we have m minus 1 for n minus k minus 1. Okay, so this is what you need to do, right? Okay, all right. So here okay, this is done. Okay, this is for m. Okay, these are the number of choices for m. So here if you see in this case also, here and here, okay, we are doing the segments. Okay, and also here this is just for the choices. Okay, so here there are different number of ways also to choose the equal positions, right? And the first segment choices also. So how many ways to choose the equal positions here? So that is nothing but you can say total among these is n minus k. Among n minus k, we are doing the partitioning over n minus 1 minus k, right? Okay, n minus 1 minus k. So these are nothing but the number of ways. Okay, this is nothing but the number of ways. I can also write it like this, n minus 1 uh, k. Okay, I can also write it like this. Why I can write it like this? Let's understand this here. Okay, so few concepts that you should know. The multiplication principle first, also called the fundamental principle of counting states. So if a task can be broken into multiple independent stages and each stage has a fixed number of choices, then the total number of ways to complete the task is the product of the number of choices at each stage. Okay, so example, let's say you have 3 shirts and 2 pants. Okay, 3 shirts and 2 pants. Okay, so here you can do the combination of this. Okay, this and this. Okay, this is your one choice. Okay, this is other choice, this is other choice, total 6 now. So then the number of outputs you can fear is 3 shirts into 2 pants. Okay, that's why multiplication is doing, we are doing. So why it is called a principle? Because it's a foundational rule that help count the total possibilities when stages are independent. Okay, so that's why here stages are independent, right? Okay, so that is why we are doing this, m into m for 1. Okay, and for remaining m minus 1 into n minus k minus 1. Okay, right? So these are different. Okay, but here also different positions we have to choose, right? So here let's understand this binomial symmetry or entity. So n by r, we can treat this as n by n minus r. Okay, so what is this meaning? The number of ways to choose r elements out of n is the same as the number of ways to leave out r elements, that is choosing the remaining n minus r. Okay, so if I say you have 5 books. Okay, out of these 5 books you have to choose just 2. Okay, so you are going to do 5 here, 5 factorial, 2 factorial and 3 factorial. So you are going to get output as 10 only, right? 5 into 4 and here into 3 into 2 into 1, and here 3 into 2 into 1, and here 2 into 1. Okay, and here this is going to cancel out, this is going to cancel out, this you are going to 10. Okay, so this is choosing 2 books out of 5. Same way, if I say that how many books you are not choosing, you are not choosing 3 books out of this 5, so that is also going to be same. Okay, 10 only. Okay, so let's say n is equal to 5 and you want to choose r is equal to 2 people, so you are going to 10, get 10, and here choose the 3 to leave out same thing, right? So algebraic justification is this, right? So same formula is coming out, so we can write it like this. Okay, so here this is nothing but, okay, this part is nothing but, this is nothing but the ways to choose the equal positions. Okay, these are nothing but the ways to choose the equal positions. Okay, so here first segment, first time you are using this, okay, this is one way, then next time you are maybe using this one also, right? Maybe next time you are choosing this one also. So let's understand this with this example also here. So here 3 na, 3, right? 3 3 3 here. Okay, this is what you need to do, right? Okay, so here this is how you are going to do the split, right? This is how you are going to do the split. Okay, so here if you choose like this, okay, so here how many ways? uh, Here m is nothing but 2, and for the remaining part just one way. Okay, okay, 2 into 1 you are getting, okay, for this one. Okay, 2 ways, right? So here what are 2 ways? First way is this, you are going to use 2 to 1, or you can say 1 1 2. Okay, so they in total 2 ways, right? Okay, but here also among these, this is also one way now, right? This is also one way, right? So in this way also we need to calculate, right? These are different ways, right? So here also you can place like this 1 2 2 or 2 1 1. So from here also, if you treat this as one segment, so here you have two choices, and in this part you have one choices, right? Right, so here if you are choosing one, here you are choosing two, here two choices, and here in this complete part you have just one choice. Okay, so we are checking this, and then for these two also we need to check. So that is why I'm doing this. So here we are just making one line. Okay, so that I can simply say in total if you see these two are adjacent, these two are adjacent. Okay, so from n minus 1 uh, n minus 1, here I can just write c. Okay, c, and here how many number of lines that we are drawing here? N minus uh, k, we have to, k is 1. Okay, so remaining is n minus 1 minus k. Okay, and here I told you that n minus 1 minus k, right? So this is simple now. If you see this, okay, treat this. So here this, let's say this is n, this is n, this is r. Okay, so n minus r, so that is nothing but n by r now. So n minus 1 and k. Okay, we can also write it like this. So that's what we are doing, right? So I hope that this is clear. So we have to just multiply all these and we will get our output. That's it. Okay, but for that there are many things that we are using in this problem. Okay, little bit maths we are using. Okay, so let's understand few things. But the final formula that we are going to use is nothing but this one, m into m minus 1 n minus k minus 1 into n combination of n minus 1, okay, out of this n minus 1 for k. Okay, so this, or you can say n minus 1 ck. Okay, so here few things that you should know, okay, before moving further. So what is this Fermat's Little theorem? So Fermat's Little theorem is a fundamental result in a number theory. It allows us to efficiently compute the modular inverses, which is especially useful in problems involving modular division like combinations and CR mode with mode, right? So the theorem for prime mode: if p is a prime number and a is an integer such that a is not divisible by p, okay, then a of p minus 1 is going to be equal to 1 mod p. Okay, clear? So here the modular inverse of a modulo p. Okay, let's just understand this line: modular inverse of a modulo p. Okay, so a modular inverse of a, that is nothing but a minus 1 mod p. Okay, this you can write it like this: a p value p minus 2 and mod p. Okay, so you have to just, if you are getting a inverse value, so you have to just change it to p minus 2. Okay, if you making sure that p is prime. Okay, so in our case, mod p is prime only. Okay, 10 to the power 9 plus 7, that is nothing but prime only, right? So division is not directly allowed under modulo. To divide under modulo, you multiply by the modular inverse instead. Okay, so here x by mod p, so you are going to write it x y minus 1 mod y minus 1 mod p, and here just change this y1 y minus 1 as y p minus 2. Okay, that's it. So works only if p is a prime, like this, right? So here if you want to validate, okay, so we have already discussed this in some past problems also, this theorem in detail. So here also let's quickly do the revision of this. So suppose you want to compute 5 by 3 mod 7. Okay, so you are going to write it like this: 5 3 minus mod 7. Okay, right? Now here I told you that 3 minus 1 you can write it, this is mod, right? So 7 minus 2 5, 3 power 5, and here mod 7. Okay, and 3 power 5 is nothing but 243. 5 3 5 is 243. 243 mod 7 if you do, okay, you are going to get a remainder as 5 into a remainder as 7 3 are 21, 1 here. Okay, 7 3 21, 3 here, 7 4 are 28, so you're going to get 5 here. So 5 into 5 is 25. Okay, 25 mod 7 if you again do, you are going to get 4 output, right? So here see, 3 minus 1 mod 7, 3 7 minus 2, 3 5 2 4 3, 2 4 3 mod 7 is equal to 5. So 5 by 3 mod 7 is 5, here 5, 25, 25 mod 7 if you say 4. Okay, so you can also confirm this. So in modular arithmetic, if x is equal to a by mod p, so we can validate it using b into x mod p, it should be equal to a, right? So now we know the value of this b, that is nothing but coming out as 5. Okay, so here 5 into this x. Okay, so this x value is coming out 5, right? X this x value is coming out as 4. Okay, so here if you see clearly here, okay, so here in this part where you calculate 3 minus 1 uh, mod 7, okay, this part you are getting 5. Okay, you are getting 5 here. All right, okay, and now if you do b into x, okay, b dot x, so here your this b value you already know that it is 3, and x value that is coming out as 4. Okay, so x value is coming out as 4, b value you already know 3, so 3 into 4 you are going to get 12. 12 mod 7 if you do, you are again going to get 5. 5 is nothing but a. Okay, so just apply this formula. All right, so in this formula you will get the output. Okay, so both are matching, so that simply means that this theorem is correct, right? So we have to just use this, okay, to calculate the inverse, right? Okay, so you can go in detail about this Fermat Slater theorem maybe in my past videos, or maybe you can use Wikipedia, okay, if you want to understand this theorem, how we are driving this. Okay, all right, okay, so this is the formula for this one. So a p minus 1 raise a to power p. Okay, so I think I haven't discussed this. Okay, so a p minus 1 is equal to 1 mod p, right? So a p minus 1 raise a to power p minus 1. All right, so it is equal to 1 mod p. This result, the result leaves a remainder of 1 when divided by p. So example, if you can try, a is equal to 2, p is equal to 7, 7 is a prime, so 2 power 7 minus 1 is equal to 2 power 6, 64. And now if you use 64 mod 7, so you are always going to get 1. Okay, so that is why we are saying it like this. All right, so it works. So why it is useful? Because of this rule, a minus 1 it is equal to ap minus 2 mod p. This is how we compute the modular inverses when working with prime modules. Okay, so where we need this? Okay, so if you are applying these formulas, okay, ncr, so here you have formula like, let's say your n is equal to 5. Okay, simple, let's take simple. Okay, r is equal to 2, so here you are going to calculate like this now: 5 uh, 2 and 3. Okay, and with mode with 10 to the power 7. Okay, this is also required mode, or I can do like write like this: mode with 10 to the power 7. Okay, so in these cases, okay, you have to solve it. Okay, in these cases you have to just calculate this. 5 is nothing but the factorial of 5, and here this 2 if you take it above, so you are going to write inverse of factorial. Okay, factorial inverse you can say of 2, inverse factorial of 3, and then do the mod. Okay, so from here you can directly get the values, okay, using this Fermat's little theorem. All right. Okay, so now all right, so here you are doing this a is equal to p minus 2, right? That simply means a's power something is there. Okay, now here there is a one concept called fast exponentiation. Okay, we have already discussed this in past as well. Okay, binary exponential. So you want to compute something like a power n mod m. Okay, so now here n value is very large. So are you going to do like this, a into a into a into n times? That's too slow, right, for large n value, right? So what is going to be our idea? Our idea is going to be this fast exponentiation. Okay, use divide and conquer plus modulo at each step. Okay, so here if n is even, so I can also write it like this now, a n power 2 multiply by 2. Okay, this is same thing, right? So here 2 power 10 if it is there. Okay, so I can also write it like this, 2 10 by 2 5. Okay, then this square, complete this square. Okay, 2 power 5 calculate and then do the square. That is easy, right? Okay, and if n is odd, so in this case, so you see n is odd, so I can also write it like this, take 1 2 outside and the remaining 2's are 4. Okay, so 4 divided by 4. Okay, so I can also write it like this. Then from here also I can use this even logic. Okay, 2 power 2 square. Okay, then from here also if you see I can write this even only, so 2 and here 2 power 1. Okay, and here 2 and overall 2, right? So here this is done, right? So now if you calculate this 2 power 4 4. Okay, now if you solve it, this 2 power 4. Okay, so this is odd. Okay, this is odd. So here if you can also write it like this for more simplicity, 2 power 0, right, dot 2. Okay, this is also you can do right here. So this is how you can solve this. Okay, you are going to break this into a little bit, so it is going to just of log n. Okay, so this is the function to perform the fast exponentiation. Okay, x bar n with mod. Okay, so if your n becomes 0, okay, so here your n becomes 0, then from here you are going to start returning 1. Okay, so 1 you are going to turn 1 into 2 is 2. Okay, then 2 power 2 you have to calculate, that is 4. 4 into 2 16. 16 into 2 32. You are going to get the output of 2 power 32. 2 power 5 32, and this you know is 32. 32 square you are going to do, that's in 32 into 32. So you are getting the answer very quickly instead of 2 into 2 into 2 into 2 into 2 into, right, like this. Okay, so here we are doing the half. Okay, let's say this is your q power function. Okay, x power n we have to calculate. Okay, all right, so first we are doing the half, right? And here we are going to get the result of this, half into half. Okay, right? So half into half, 2 power 5. Okay, so that simply means 2 power 5 into 2 power 5. Okay, half into half. All right. Okay, and if it is odd, then we need to take the outside. Okay, to in the starting it is 2 power 10 only, even only, then don't need to do that. But if it is odd, okay, then in that case we have to update the result as result into again one more value of x, right? 2 power 5 it was there, so 2 into 2, 2 into 2 we did. Okay, for 2 into power 5, right? But one 2 is still remaining. Okay, so that is why multiply by 2. Okay, then update the result like this. So in the end you will get the one particular result. Okay, this is for fast explanation. Okay, right? And now inverse factorial also. Inverse factorial, how you're going to do that? Inverse factorial, so this okay, so you are dealing with this formula, right? NCR. So you are calculating the factorials of 5 and 3 and 2. Okay, so here do you are going to calculate the factorial of 5. That is very simple. 5 into 4 factorial. So if you know the value of 4 factorial, you can get the answer as 4 of for 4 is 4 into 3 factorial. For 3 factorial, you if you know the value, 3 factorial is nothing but 3 into 2 factorial, right? 5 into 4 into 3 into 2 factorial. For 2 factorial also you know the value, that is nothing but 5 into 4 into 3 into 2 into 1. Output is 20, 120, I think, right? 120. But here this is inverse factorial. Okay, 3 minus 1 factorial you need to calculate 2 minus 1 factorial you need to calculate. Okay, so for inverse ones you are using this, okay, format little theorem, right? Okay, a minus 1. Okay, but here we need the factorial also, no? Here we need the factorial also first. Okay, 3 minus 1 factorial. Okay, 3 factorial minus 1 you can write like this also, I think. 3 minus 1 factorial. Okay, like this. 2 minus 1 factorial. Okay, so for this inverse also you need the value of factorial, right? So how you're going to calculate that? So inverse factorial of I minus 1. Okay, let's say this is a value. So inverse factorial of I minus 1, so that simply means I minus 1, this factorial. Okay, so you are going to write like this, I minus 1 if you take it above, okay, and factorial, then do the inverse. Okay, that's what. Okay, minus 1, right? So this is what you need to do, right? So given that we already know that inverse factorial of I is equal to I factorial inverse. Okay, inverse factorial simply means here like this. So that simply means if I take it above, so I inverse I factorial and then minus 1. Okay, so now see here a relationship between them. Okay, so here I factorial I can write it like this, I minus 1 factorial and multiply with I. So that simply same means same thing, na? Right? I minus 1, right here. See 5, how you write 5? You write 5 as 5 into 4 factorial, right? So that's what I factorial. If you want to calculate 5 factorial, you are writing 5 into 4 factorial. So that simply means I factorial is equal to I minus 1 into I minus 1 factorial into I. Okay, that's simply correct. Okay, now if you divide both sides by I, so you are going to get here I and here divide by I, you are going to cancel out this. Okay, so you are going to get this I factorial by I, okay, is equal to I minus 1 factorial. Okay, this part is done. All right, now you can also write it like this. If you do the inverse, okay, so here if you divide both sides by 1, so you are going to get I minus 1 factorial inverse. Okay, and in this side I is going to go above, and here for this I factorial it is going to get the inverse. Okay, you are going to get this. So from here we know that I minus 1 factorial's inverse is equal to I factorial minus 1 into I mod mod. Okay, so for I minus 1 factorial, okay, we are using I factorial inverse. For I minus 1 factorial inverse we are using I factorial inverse. So if I am going to calculate this, it's good if I already know the value of this I factorial in the past, right? So from here I'm going to drive one logic that I'm going to run the loop backwards. Okay, so using Fermat's little theorem I'm going to calculate this value first. Okay, Fermat's little theorem, I'm going to get the calculate of this one value first, then after that for the other values, okay, like for 10 I'm going to calculate, for 9 8 for 10 I'm going to calculate using Fermat's little theorem. For others I will simply use this formula. Okay, because this is going to give me very fast result, right? Very fast result. For this one I will use FLT, for Fermat's little theorem. In Fermat's little theorem we are using Q power and all, but for the remaining ones I can simply use this formula. Okay, that is the reason why I'm showing this. Okay, so we will understand this in code much better. Okay, let's write the code. Let's write the code. Very simple, nothing complex here. Okay, I will write all the lines in very details. Okay, so here first what is our formula? Okay, so let me add the comment here. So M into C, okay, from n minus 1 comma k. All right, and here after this for the remaining we have choice m minus 1. Okay, m minus 1, and we are doing this m minus 1 for how many? Into n minus k minus 1. Okay, you know that why we are doing this power. Okay, I think I told you, but I'm not sure. So here if for this is m, for this one is m minus 1, for this one also is m minus 1 only, na? So m minus 1 is for how many? M minus 1 is for n minus 1 minus k, n minus k minus 1. Okay, that's why I'm doing. Okay, and we already know why we are doing multiply. Okay, right? here you have 5 choices, here you have 4 choices, here also you have 4 choices. So if for this you have 1, okay, so here 4 choices, you can say do the square now, 4 into 4 instead of 5 into 4 into 4, you can write it like this. So if this value is k, and this value is nothing but n minus k minus 1 now, right? So here in this case, if you see, n is 5, 5, this case 2, 5 minus 2 is 3, 3 minus 1 2, that is right now. Okay, that's it, that's why. Okay, this is done. Here n minus 1, let's use some more, no issue, but just okay, right, this is done. Okay, so now here first, ways to choose equal positions, how many ways to choose the equal positions. Okay, so for that, long ways to choose equal positions. Okay, so that is nothing but combination, right? Here simple, this formula you can apply, n minus 1 comma k. Okay, n minus 1 comma k. So that is nothing but ways to choose the equal positions. Now first segment choices, how many first segment choices are there? So long first segment, I can use here short variable also, but just for your understanding, right, because I am teaching this, so it's good if you understand what are these variables doing. Okay, so first segment choices is m, right? And now remaining segment choices. Okay, so here long remaining segment choices is equal to, here I'm just going to call this fast exponential function. Okay, so because we are doing the power now, for how many, for m minus 1, okay, choices we have, right? M minus 1 ways we have can choose, for how many, n minus k minus 1. Okay, done. And then here we have to just calculate the result. So how we are calculating the result? So result is nothing but the ways to choose, okay, this ways to choose equal positions multiply with first segment choices. Okay, first segment choices, and here let's do the mode also now, because value is going to be very large. Okay, so here you have to write mode with mod. Okay, I will create this variable mode, and then this is pending, still pending remaining segment choices. Okay, update the result as, okay, a result as whatever the result that we got above. In that just multiply this remaining segment choices. Okay, remaining segment choices, all right, and again do the mode, right? Just copy this, paste it, done. Okay, and in the end you have to just return the result, return result. But here if you notice one thing, we are taking long, right? And it is expected, right? We are getting very large values, right? But return type is int. Okay, so just change it to int. So here in the end just change it to int. Okay, since we are doing the mode only, right, we have to return the modulus value only. So now return it to int. Okay, that's it, that's it, right? So now we have to just solve, write this code comp. Okay, and this code q power, you already know this q power. Okay, you already know about this q power, this code. Okay, you already know this. Okay, so here first let's create few let's write the code for this code. Okay, let's start from mode only. Okay, so define the modulo constant. Okay, so define the modulo constant. Okay, so here static final int, we are taking capital, right? Mod is equal to uh, int 10 power 9. Oh, you can write 1e 9 plus 7. All right, and this is done. And here we have to take the maximum size for the factorial arrays. So here if you see in the problem statement, n values until 10 to the power 5. Okay, so let's calculate the factorial of all the numbers from 1 to 10 to the power 5. Okay, 10 to the power 5 means okay, let's think that. Okay, so here maximum size for factorial arrays, right? So here maximum size for factorial arrays. Okay, so you can say here static final int maximum size, so that's for 5 now. 1 1 2 3 4 5. Okay, done. Now arrays to store the factorial and inverse factorial modulo mode. Okay, so here let me write the comment also. Arrays to store factorial and inverse factorial modulo mode. Okay, this is done. This is what we need to do now. So here for that here what you need to do, static. Okay, now we have to create one array, right? In that we have storing. Okay, size we already know, that is nothing but mx. Long fact is equal to new long and here mx. Okay, and here same thing, you can copy this and paste it here for inverse factorial. Okay, inverse, and let's make it capital. Okay, inverse factorial, done. All right, now so we have to create the static initializer block to pre-compute factorials and inverse factorials. Okay, so in competitive programming it's good if we already know the results of factorial and inverse factorials beforehand, okay, instead of calculating them again and again. Okay, so it's good, okay, because it is going to give the fast results. Okay, if I already know the values of the all the factorials and the inverse factorials in the initial beginning only, right? So here what I'm going to do, you can write static initializer block to pre-compute factorials and inverse factorials. All right, so here what you need to do, static. Okay, and here you know that factorial of 0 value is nothing but 1. Okay, this we already know, right? And now we have to calculate the factorial value for others. Okay, so simply we are going to run loop factorial of I 1 and until it's going to run until mx, and here I plus plus, and here factorial of I is nothing but factorial of I minus 1, factorial of I minus 1, right, into I, right? So 5 is nothing but 5 in 5 factorial is nothing but 5 into 4 factorial, right? Okay, so that's the reason. So here side by side do the mode also, right? We don't need the bigger values. So here mode, done. Okay, this is done. Now this is done. Okay, and now we have to compute here what we are doing here, we are just pre-computing pre-compute factorials. Okay, done, right? And now we have to just compute the inverse factorials. Okay, so here compute inverse factorials. Okay, so now here if you see here in the end, I explained that for 10, okay, for the last value I'm just going to use Fermat's little theorem to calculate the inverse factorial. Okay, so here inverse factorial of last value, that is nothing but mx minus 1, okay, is nothing but q bar okay, this function I will write, okay, q bar, and here factorial of mx minus 1, okay, and for here we have to do the mode with mode, we have to do the power with mode minus 2. Okay, so this power mod minus 2. Okay, so this is how we write the Fermat-Slater theorem. Okay, now here I am calculating for mx minus 1. Okay, so now from here I can simply calculate for the previous ones. Okay, instead of calling this inverse factorials of Fermat-Slater theorem again and again, I can simply run one reverse loop. Okay, for int I is equal to mx minus 1, right? I mx, not max, mx minus 1, and here I is greater than 0, and here I minus minus, and here inside this you have to write inverse factorial of I minus 1. Okay, I minus 1, so this is nothing but your inverse factorial of I, okay, I into I, and then simply mod. Okay, that's it. So you already know this. From where? Here we are deriving this final formula. Okay, this we studied how we are getting this. Okay, right? All right. Okay, so that's why we are using this. Okay, so instead of calculating like this for all the ones, we can simply use this loop. Okay, it is fast, linear, right? Okay, so this is done. Now this is done. Now only few things are pending. One is this q power I need to write, one this comp. Okay, very simple. Okay, q power, very simple, you already know this. So here I can write the first comment. Okay, so that is nothing but function to perform fast exponentiation. All right, so that is nothing but x bar n mod. Okay, so let's write this static long q bar. Okay, and here long x long int n. Okay, int n. All right, and here take the, okay, so here what you can do, uh, you can use there are two ways actually. You can use a recursive method also, you can use iterative approach also. So let's write a recursive. This you already know, right? If n is equal to 0, then from here simply return 1. Okay, and then take half as here q bar. Okay, now here x is going to remain same, but here you are passing n minus n divided by 2. Okay, right? And result is equal to nothing but half into half. Okay, and here you have to do the mod. Okay, and here if you have to check if n modulus with the 2. Okay, if this value is equal to 1, then in that case you have to simply update that. If that means if it is odd, then you have to update the result as result into x, and here just with mod, right? And from here you have to simply return the result. Done. All right, okay, this is done. Now only few lines are pending, only few, two lines, that's it. Okay, we have to just write this comb. Okay, how it is working. So that is also very easy, you already know the formula. Okay, long comb, and here we have two values, int n and int r. Okay, so inside this what you need to do. Okay, so function to compute this, let me add the comment also for better understanding. Function to compute ncr modulus with mod. Okay, mod using pre-computed factorials. Okay, using pre-computed factorials. Nice. So here simple, nr. Okay, so that simply means n factorial, n minus r factorial, and r factorial. I can say factorial of n, inverse factorial of n minus r, inverse factorial of r, right? So this is what I'm going to write here. That's it. So here we have to just simply return, okay, but we need to return factorial of n, okay, into inverse factorial of r, okay, and here just do this part mode, okay, and then here just multiply it with inverse factorial of n, uh, inverse factorial of n minus r, okay, and do the overall mode, okay, mod capital. All right, this is done, and that's it. That's it. I don't think we are missing anything now. That's it. Only few lines of code, right? Now let's run the code. Okay, let's see if there is code issue. We'll try to fix that. Nice. Oh, the test case has been accepted. Wonderful. Now let's submit it. So see, our solution is accepted, right? Okay, so I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.